Transformer architecture-based models such as LLMs are not perfect. I'll open this lesson with a quick recap of how models use their knowledge to generate responses. Then I'll walk you through 6 common known challenges with LLMs. For some of these challenges, I'll demonstrate interesting model behavior. Models acquire world knowledge from the data used for training. This training corpus contains the source knowledge, and this source knowledge is encoded in the model in the form of parameter weights. This knowledge is static as the weights stay the same unless the model undergoes fine-tuning, and that will lead to the change in the weights of the parameters. And that means there will be a change in the knowledge. Transformer models exhibit the capability to produce creative and novel outputs such as generating poetry or crafting marketing slogans. This feature distinguishes them from the traditional machine learning models. The key point to keep in mind is that the generation of the output relies on the model's utilization of its parametric or static knowledge. Time for a quick question for you. What will be the model's response when presented with a topic that it hasn't been trained on? Select the appropriate choices. If you selected first and the second choice, then you are right. Let me explain in the reverse order. The last option is incorrect. Models don't always provide an output that is correct. Second option is correct, as newer models with appropriate prompt may respond with "I don't know" or something similar. The first response is also correct. Models do have this tendency to give out incorrect information as a response. This behavior of models is common across current generation of models. Hallucination is commonly observed phenomena in large language models wherein the model produces a factually incorrect response, and it produces it in a very confident manner, such that it appears to be correct. I've put together a notebook to demonstrate the challenges with LLM. This notebook is available under the folder GenAI Fundamentals. You can also open this notebook in Google Colab by clicking the button Open in Colab on the page LLM Challenges under the section Fundamentals of GenAI in the course guide. In this notebook on LLM challenges, you will see that I'm setting up the environment, and then I'm setting up an array with 3 models. The idea is that we're going to try out the code in this notebook with different models. So let's start with hallucination. I'm putting together some input text, define LLM in the context of biology, and I'm using model number 1, which is Mistral AI model. Let's check out the response that we'll get by running this model. So here it says, as Master of Laws degree with a specialization in the field of biology, this degree is designed for individuals who have a background in biology and an interest in legal aspects. Now, this is clearly not accurate. In fact, I checked it online and I found that this is meaningless. So this is an example of hallucination. I'll suggest that you try out the other models with the same input and see what happens. Challenge number 2 is related to the fact that model's knowledge is dated. Once the model is trained, its static knowledge does not change, and this is referred to as the cutoff point. In other words, model will not be aware of any event after the cutoff point. In fact, some models, like ChatGPT, when asked, share their cutoff date. Some of the source knowledge may be dynamic. For example, a bot cannot suggest whether it's a good idea to buy a stock in a company or not, as the market conditions may have changed, company may have gone bankrupt or boomed since the model's cut off. Model's knowledge will no more be accurate, as the real-time updates are typically not fed back to the model for retraining or fine-tuning. Let me show you this behavior. In this demo, I'll be using Falcon 7B Instruct, which is a fine-tuned model published in 2021. The question that I'm passing as input to this model is, as of today, who is the Prime Minister of UK? Let's run it, and it says the Prime Minister of UK is Boris Johnson, which is incorrect. So, couple of things to note here. The model doesn't have the concept of as of today. It doesn't understand that. Second thing is that when it was trained, it knew that Boris Johnson was the Prime Minister of UK, and it just ignored everything else and responded by using the knowledge that it has. I suggest that you try out other examples and other models on your own. Third challenge is referred to as the missing context. To describe it, I'll use an example. Let's say an e-commerce vendor built a chatbot using a foundation model. That is, they're using a model that is pre-trained only on public data. How do you think this chatbot will behave when the customer will ask this chatbot questions that requires deeper knowledge of the business model, policies, and operational data such as product catalog? For example, the customer may ask, "What is your return policy?" or "Do you sell a specific model of vacuum cleaner?" The bot that is using the LLM does not have the enterprise context, and it would respond back with hallucinated or imprecise response. Let's check it out. In this demo, I'm using the Mistral AI model. The question I'm asking is, "What is your return policy?" And when we run it, it says we offer a 30-day return policy for all of our products. Now, this has no bearing with the enterprise policy for returns. This is a generic response that the bot will give out to anyone who's using this specific model for building a chatbot. Let's try out another question. In this question, we are asking, "Do you carry the Acme brand Robo Cleaner?" Let's see what the bot says. And here, as you can see, yes, we do carry Acme Robo Cleaner. I'm not even sure whether such a product exists. So anyway, the idea is that without the context, the model will respond back with imprecise responses that may have no bearing with the business model of the enterprise. As models derive their knowledge from training data, the presence of biases in that data inherently embeds biases into the model's parametric knowledge. These biases may manifest in diverse forms, including racial, gender, political, religious, etc. Consequently, models trained on biased data sets tend to generate biased responses. Acknowledging this challenge of bias, some model creators proactively address it during pre-training. It is imperative to avoid the use of biased models, and if unavoidable, meticulous measures must be implemented to mitigate and prevent biases in their applications. To demonstrate biased behavior of a model, I'll use the model OpenLlama 3B v2, and the input that I'm providing is, "For the engineering jobs, we should only hire men because," and I expect the model to complete this sentence. Let's go ahead and run it, and here is the completion. They are more likely to be able to do the job, and you can read it yourself, but the whole idea here is it is a biased response. You may check out other input text and other models as well. The next challenge is the lack of transparency. Transformer models are complex, and it is virtually impossible to understand what process and information they have used to produce a response. This lack of transparency is a big concern to enterprises, especially to the enterprises that are in the regulated industries. In sectors such as finance, healthcare, and others, where regulations and compliance standards are stringent, there is an increased emphasis on understanding and explaining the decisions made by the large language models. This is an active area of research. Researchers are developing explainability techniques to interpret and understand the decisions made by LLMs. This last challenge is tied to the fact that models function independently. They do not have the ability to take any action or engage with their operational environment. Let me explain it with an illustration. Let's say you built a chatbot. Weather information is dynamic, that is, it changes all the time. So if someone asked, "How is the weather in New York City?" Though there are multiple sources of weather data that are readily available, the model will not be able to use these sources of data, and as a result, the response may be hallucinated or imprecise. Models are stateless. They do not have a memory to hold any kind of interaction data, and there is no concept of sessions. Compared to other challenges, this is not a big challenge, as this deficiency can be addressed in the application logic. You will learn about it in details in a later section. In this lesson, I covered common challenges with LLMs. Hallucinations refer to a phenomenon in which LLM generates factually incorrect responses. Model's knowledge is not updated after the cutoff point. As a result, model is not aware of any event that occurs after its training. Model produces imprecise responses if it doesn't have the context. Models have biases that they acquire from the training data. It is hard to understand how a model generated a response, that is, there is a lack of transparency. Models cannot interact with their operational environment. In the next lesson, I'll provide you an overview of techniques used for addressing these challenges. As you will progress through the course, you will get hands-on experience with design patterns and code that will help you develop GenAI applications that can overcome these challenges. Happy learning, and I'll see you in the next class.